Okay, so let's go through our simple harmonic motion worksheet. I'll first go ahead and read the problem, and then we'll go ahead and answer, I think, 17 questions related to this one single problem. And so that tells us something about oscillation problems. Everything is related to everything else, and we can answer a lot just by being given just a little bit of information about the system. So I'll go ahead and read it. You are studying the motion of a cart on a horizontal surface. The cart is attached to a spring with spring constant 128 newtons per meter and is undergoing simple harmonic motion. You observe that the displacement of the cart is described by the following equation as a function of time. X as a function of time is equal to 0.3 meters times cosine of, in brackets, 8 radians per second times time plus 2.1. That's all in SI units. So that's our problem statement. Now we have to read this in detail maybe a couple times and think about what it means, and then go ahead and answer all of these questions. So if you need to pause the video, works for it on your own, and when you get stuck, unpause and see if you can get a little bit further. But I've drawn a picture of the situation. We have a cart on a horizontal surface, so you can think about the air track in lab. So the cart is able to move back and forth on this horizontal surface without any friction. So we'll call that direction in which the cart is moving the x direction. We'll define x equals 0 to be the location where the cart is attached to the spring and the spring is neither stretched nor compressed. So that's what we call x equals 0, or equilibrium point. So since the spring is not stretched nor compressed, there is no force acting on the cart when it's at that location. We'll define the plus x direction to be stretching that spring and the minus x direction to be compressing that spring. So that's our situation. This is our typical simple example of an oscillating system. And we know that the cart is going to be going back and forth between two locations as it oscillates. So it's going to be oscillating back and forth between its maximum amplitude and its minimum amplitude. So that's kind of our picture of what's going on. And this cart is going to be oscillating back and forth between these two locations as a function of time. And in fact, they gave us the exact equation for how it's going to behave as a function of time. We know that the exact equation for its position at any moment in time is this equation they gave us. Okay, so perhaps I'll write that without units for now. Just you can add units on your own just to keep it nice and simple for you to see it there. So you can go ahead and graph this equation if you want. In fact, I have it graphed already right here. So as we would expect, as a function of time, the position is oscillating. So the position of the cart is plotted on the y-axis here, and time is plotted on the x-axis. So you can see that this cart is oscillating back and forth in its position as a function of time between some maximum position and some minimum position. And we can see at time equals 0, the cart is not at its maximum position, which tells us that we can't use a normal cosine function to describe this. We have to shift our cosine with the phase constant. And in fact, the phase constant in this problem is 2.1, which shifted our cosine for us. And now our initial position is somewhere around negative 0.15. So that's a picture we can have in our head as we try to answer these questions. So let's go ahead and try to answer this. So what is a cart's amplitude? That's our first question, question A. So to answer this, we have to think about the form of this equation. Right? Amplitude is the maximum position of the cart as it oscillates back and forth. So what is the biggest this equation can be? Well, we know that cosine, or everything right here, cosine, only oscillates between 1 and minus 1. The biggest cosine can be is 1. So the biggest that this function can be is given by this number that's out in front, right? That number times the biggest cosine can be, which is 1, is always going to be our amplitude. So it turns out that that number, which is out in front of that equation, is always going to be our amplitude. And so we can write that down. Just by inspection, we know that the answer here is that the amplitude of this glider as it oscillates back and forth is 0.3 meters. In fact, we can probably just write down our general equation for the position of a oscillating object as a function of time, because we have that on our equation sheet, and it's given by an equation like this. This is an equation on our equation sheet, which can describe any simple harmonic motion. And so by inspection, I can right away recognize that whatever is in front of the cosine is my amplitude, and so that must be 0.3 meters. Whatever is in front of the time inside the cosine has to be my omega, my angular frequency. So my angular frequency must be 8 radians per second. And then whatever is added to that within my bracket must be my phase constant, my phase shift, or phi. And so that, in this case, is 2.1. So we can recognize that those are all knowns to us at the start of this problem. So right away, we can answer part B. What is the Karts angular frequency? That's given by the symbol omega. And again, by inspection, as we highlighted in green there, the angular frequency must be 8 radians per second. Okay. Great, so we can move to part C. What is the Karts frequency? Well, we know that frequency is related to angular frequency, and in fact, there's a simple equation on our equation sheet that relates those. All right, that equation is, maybe I'll switch colors here. Omega is equal to 2 pi times frequency. So there's a relationship there between frequency and angular frequency. So we can then go ahead and write frequency as being omega divided by 2 pi. So I just have to divide 8 radians per second divided by 2 pi radians, and I end up getting 1.27 per second, or 1.27 hertz. Okay, so that's our frequency. We know that per second has a name, and that's called a hertz. Either is okay in your answer, but just to recognize what a hertz is, it's equivalent to 1 per second. So what is a Karts frequency? Part D is what is the Karts period? So we have an equation for period that relates it to frequency. Right? Frequency is how many oscillations per second. Period is the amount of time it takes to go through one complete oscillation. So those are very related concepts. So we can go ahead and just use this equation directly to solve. 1 divided by 1.27 hertz is equal to 0.785 seconds. So the period of this oscillation is 0.785 seconds. Okay, that's how much time it takes to go through one complete cycle. And we can perhaps view this really quick if I add that plot over here, and we can just take a look at this is plotting this equation, and we can see that we're starting off at this position at time equals 0, and a period is how long does it take to go through one complete oscillation. So from this initial position to come back to the same position while moving the same direction. So by starting here, it's as a function of time moving out towards a more negative position, and then it's moving back. It returns to its original position, but that's not a complete cycle, right? That's just passing through our original position going the other direction. And we oscillate all the way out to our other maximum position, and then we oscillate back until we get to here, right? So that amount of time is one complete cycle, right? That's one cycle. The time it takes to do that one cycle is our period, and we can see that it matches our expectations of being about 0.785 seconds. So that's how much time one period is in this case. So, okay. And we can also see from the graph that our amplitude's answer was correct, right? Our amplitude is 0.3 meters. This is oscillating between negative 0.3 and plus 0.3 as it oscillates back and forth. So I'll clear this all out so we can see the whole worksheet and keep on moving here. So part E, what is the Karts maximum displacement? Well, that's a pretty simple answer because by definition, amplitude is the max displacement, right? We want to know the max displacement. What is the maximum position of this glider as it oscillates back and forth? And by definition, that is our amplitude. So that's an easy one to answer. Okay, so we know that. Next, we get to part F. What is the Karts maximum speed? So we have to be a little bit more smart now about answering this question. First, what is the Karts maximum speed? The first thing we have to recognize is where is that going to happen? Right? This object is oscillating back and forth between A and minus A, just oscillating back and forth. So where in that oscillation is it going to have the maximum speed? Right? And we know conceptually that it must happen right here, right? At x equals 0. that's where Vmax has to occur. That's where the maximum speed is going to occur. All right, why is that? Because we're stretched out to our maximum position. At that point, its velocity is equal to 0, right? And then the spring is going to accelerate it back towards the equilibrium point, right? And it's going to accelerate and accelerate and accelerate and accelerate until it gets to the equilibrium position. Once it passes that position, it's going to start slowing down, right? The force is going to switch directions and start slowing it down. So conceptually, we know that the fastest it could possibly be moving is when it's passing through the equilibrium point. That's where the maximum velocity has to be. Okay, so given that, we know that conceptually, so how are we going to solve this problem? Well, there's two ways we can do this. The first method is using energy concepts, and so let's do that. So using energy, we know that the energy of the car at any one location has to equal the energy of the car at any other location, or the energy of the car at any moment in time, time 1, has to be equal to the energy of the car at any other moment in time, time 2, right? How do I know that? Because the system is frictionless, so there are no non-conservative forces in the system. Energy must be conserved. The only forces that we're dealing with here are the gravity, which is canceled by the normal force, and then we have the force of the spring, which is a conservative force that we defined a potential energy for. And since that's the only force, there's no friction, there's nothing taking energy out of the system, there's nothing being adding energy to the system, and it must be the case that the total energy is conserved or constant. So I can pick any two moments in time and say that their total energy at those two moments must be the same. Right? Okay, so what is our total energy? Energy is kinetic energy plus potential energy. That's what our total mechanical energy is. And so I can write down an equation for that. What is my total energy at time 1? Well, it must be just the sum of my kinetic energy at time 1 plus the elastic potential energy at time 1. And we have an equation for both of those things. At some other moment in time, my total energy is the same thing, right? It's the sum of these two types of energy. So my kinetic or potential energy may have changed, but their sum cannot change. That's what energy conservation means. And sorry, this should be a 2 here. So, all right, we just now have to decide what is our time 1 and what is our time 2. So we know two special moments in this oscillation. We know at this position, at x equals a, we know the velocity is equal to 0, which means the kinetic energy is equal to 0 at that location. So if I decide this is time 1, since kinetic energy is 0, all of my energy is potential. So I'm going to decide that's time 1. Right? If that's time 1, then my velocity is 0 at that moment, and all of my energy is potential. And in fact, I know what it is because I know my spring constant, and I know my position at time 1 is equal to my amplitude. Okay, so that's great. That's all I need on my left-hand side of the equation. Now I just have to decide what is my time 2. Well, my time 2 is what we've already identified as a moment in which we're moving fastest is when we're passing through the equilibrium point. Right? Time 2 is when we have maximum velocity. So I'm going to set that to be time 2, and we can note that our position at that moment is 0. So if our position is 0, that term goes to 0, and all of our energy is kinetic at that moment. Right? And that V2 I can in fact just rename to be Vmax. Right? That's the maximum speed. At that moment in time is the fastest I'm going. So, okay, we can see here that we have 1/2 on both sides, so I can divide both sides of the equation by 1/2, and those terms go away, and then I can solve this for velocity. Okay, velocity is equal to k over m times a squared, and then the whole thing square rooted, okay? Or square root of k over m times a. So we can do that math, and we can solve an equation for our maximum velocity. But okay, we know our amplitude of our oscillation, we know that, but we don't know k or m, right? At this moment, we do know k, I'm sorry, we don't know m yet. Later on this worksheet, we're going to solve for m, so we could solve for that now. But we could also recognize that in oscillations, there's a relationship between k and m and the angular frequency. That's one of the important equations on our equation sheet. Omega is equal to the square root of k over m. And so we do know omega. So let me just rewrite this. Vmax is equal to omega times A. And we know omega is equal to 8 radians per second. We know the amplitude is equal to 0.3 meters. And so that gives us, when we do that mass, that Vmax is equal to 2.4 meters per second. Okay, great. We found the maximum velocity, and that's our right answer. So that's really wonderful. Now, that method of solving this is makes a lot of conceptual sense. Energy conservation is a tool we know how to use very well at this point, and that's a great way to solve this problem. But let me quickly show you another way to solve it. And I'm going to just erase this. All of this past work is recorded in the video here, so I should be okay with erasing this and show you method 2. Right, what is method 2? Well, method 2 is based on the fact that we know the position at every moment in time is given by that equation listed above, right? So it's something of this form. Right? We know this exact equation. So I can figure out the velocity at any moment in time by just taking a derivative of this. By taking a derivative of cosine, I get a negative sign. And then taking a derivative of what's inside the brackets, that omega t, taking a derivative of that, I get omega. So I got minus omega times A times sine omega t plus phi. So that's our velocity at every moment in time. We know it. We could plot it if we wanted to and figure out what the maximum velocity is. But we can also note that this sine, is always oscillating back and forth between 1 and minus 1. So when sine is equal to minus 1, we then have the case that Vmax is just equal to omega times A. Right? We can note that the biggest this thing can be, this whole term, is given by that thing out in front of the sine, because sine is stuck between 1 and minus 1. So the biggest this is going to be is omega times A. So we're going to get exactly the same answer as we did before. Omega times A, so that's 8 times 0.3, or 2.4 meters per second. Okay, so two different ways to solve that problem. And both are excellent methods. And so that's a good practice. All right, part G, what is a kart's maximum acceleration? Okay, good question. So first we have to think about it conceptually. When does the maximum acceleration occur? Right? As this thing is oscillating back and forth, when is it going to have maximum acceleration? Right? Well, we know that the oscillation back and forth is based on the fact that we have a restoring force, F equals to minus kx. Right? That's our restoring force. That's what's making this thing oscillate. And so the acceleration is just going to be a result of that force. So asking when is the maximum acceleration is the same question as asking when is the maximum force. And so we can see from this equation that the maximum force, the maximum magnitude of the force, is going to be when the position is at its maximum positions, right? Either we're at our maximum amplitude A or at our minimum amplitude minus A. So the biggest force is going to be when we're at our max amplitude or minimum amplitude, and that's when we're going to have the biggest acceleration. So that's an important conceptual fact. And so we could just use F equals ma to solve this problem, right? So method 1 is F is equal to ma. F is equal to minus kx. That's our force, our elastic force, equal to mass times acceleration, which gives us an equation for acceleration equal to minus k over m times x. Again, we haven't solved for a mass yet. We could, but we can use the same trick we used above, that we have defined that omega is equal to the square root of k over m. Our angular frequency is related to the spring constant and the mass. And I can rewrite this as a is equal to minus omega squared times x. And so this is how the equation is written on your equation sheet. So you don't even have to derive it like I just did. But at this point, we know omega, and we know that the maximum acceleration happens when we're at our minimum and maximum amplitude. So this is going to be minus our angular frequency squared, which is 8 radians per second squared. And I'll just say my minimum amplitude, negative 0.3 meters, just to make our max positive acceleration. And when we plug in, we get 19.2 meters per second squared. So that's the answer to part G. Before I go on, let me show you another method of solving the problem. So let me erase that. Let's see if we can get the same answer. I'll say method 2 with this problem is to do the same method 2 we did with part F. Is that if we have an equation for velocity as a function of time, which we found in the last problem, I can take a derivative of that to get acceleration. So we get, again, derivative of sine is cosine, and then I have to take the derivative of whatever inside my sine. So the derivative of omega t is just omega. So I end up getting another omega coming out, minus omega squared times a cosine omega t plus phi is my equation for acceleration at any moment in time. I could plot this and see my acceleration at any moment, but I can then think about when is this biggest. Well, cosine is stuck between 1 and minus 1. So again, it's this term out in front, which is going to determine how big acceleration can be. So that gives us a max is equal to omega squared times a. That's the maximum acceleration we could have, which is the same answer we just had to the previous problem, to our previous method of solving this problem. So when I plug in omega, which is 8 radians per second, and a, which is 0.3 meters, I again get this as 19.2 meters per second squared. So I'll just rewrite that so we keep it here. And so that's our answer to that problem. Okay, part H, what is the position of the cart at time equals 0? Well, we have this equation that tells us the position of the cart at every moment in time. That's what they gave us in the problem. So let's write that down. It's equal to x is equal to a, I'll write it down with the actual a, I guess, 0.3 meters times cosine of 8t plus phi. So that's our equation. What is the position of the cart time equals 0? We just have to plug in time equals 0 to this equation. So I end up getting 0.3 meters times cosine of 0 plus 2.1. Sorry, I should have written down our phase constant as a number instead of a symbol for you. Okay, so we just have to do cosine of 2.1 times 0.3, and that's our answer. Right. When we do that, we get negative 0.1514 meters. Alrighty, what is the velocity of the cart at time equals 0? Well, fortunately, in problem F, we derived an equation for the velocity at all moments in time. So I can use that equation to figure out the velocity at a specific time. Right? If I know that the velocity is equal to minus omega a sine omega t plus phi, and I know omega, I know a, and I know phi, then I can just plug in velocity at time equals 0 is equal to minus omega a times sine of phi. And again, omega is 8, a is 0.3, and phi is 2.1. So I'm able to plug in directly and get my speed at that exact moment to be 2.07 meters per second. And part J, what is my acceleration at time equals 0? Well, again, we've derived earlier an equation for acceleration at all moments in time, so I can use that equation here. A is equal to minus omega squared a cosine omega t plus phi. If I plug in time equals 0, I get minus omega squared a cosine of phi. Okay, and I again know all of those terms, so I can just plug in directly and get my answer to be plus 9.69 meters per second squared. All right, so great. We're able to figure out our position, our velocity, and our acceleration at time equals 0 because they gave us an equation for our position at time equals 0. We can figure out everything about it. And we can see how important the phase constant is. It's the phase constant inside the cosine or inside the sine that determines our position at time equals 0. The phase isn't equal to our position, but the phase is what sets our position, right? The phase is what shifts the cosine back and forth, allowing us to determine what the initial position is. So with this equation, we can always plug in to get that. And again, going back to our maybe I'll have to just insert the picture again. Going back to our picture of what this looks like, again, at time equals 0, we're not at our maximum position. We're down here. And so that's exactly what we found for our initial position at time equals 0. What is right down here? We found negative 0.15. That's exactly where we are at time equals 0. So we've shifted a normal cosine. A normal cosine would be maximum at time equals 0. We've shifted it by some amount such that our initial position is properly described by this equation. So that's what the phase constant is doing. It's shifting our cosine. We can see it also set our initial velocity to be plus 2.7. Okay, and it set our acceleration to be plus 9.69. Alrighty, so let's go ahead and go to the next problem. What is the mass of the cart? Okay, we've been going this whole time without knowing the mass of the cart. How do we figure that out? Well, again, we have an equation that relates the frequency of oscillation, or the angular frequency of oscillation, to the spring constant and the mass. So that's all we need to know to determine the mass. And so this is actually how they weigh astronauts in space. They have a spring of known spring constant, and they measure the frequency of oscillation, and that tells you the mass of the person, right? And so we know this is one of our very important conceptual points about this chapter, that the properties of an oscillation are set by the object, right? It's not set by your initial amplitude or your initial velocity. It's set by the spring constant and the mass. So I can solve this equation for the mass, and we know the spring constant is 128. I know my angular frequency is 8 radians per second. I square that, and I get my mass to be 2 kilograms. Right, so I know my mass. It's been a 2 kilogram mass this whole time. And so if we know the frequency and we know the spring constant, we can always figure out the mass. Okay, what is the potential energy of the cart at time equals 0? Well, let's write down the equation for elastic potential energy. Right, so it depends on the spring constant, which we know, and it depends on our position at time equals 0, which luckily we found out in part H. In part H, we found our position, and so we can just go ahead and plug that in and square it, and we get our energy to be 1.467 joules. Okay, what is the kinetic energy at time equals 0? Well, let's write down our equation for kinetic energy. Well, luckily, we just found our mass. It's 2 kilograms. And what is the velocity of the car at time equals 0? Well, we found that answer in part I, 2 meters per second. So I plug that in. And I get my kinetic energy to be 4.2849 joules. Okay, what is the total energy of the cart? Well, there's many ways I could answer that. One way I could do it is total energy is kinetic plus potential, and I found that out at time equals 0. I know those. In part L and M, I answered that. So I can do 1.467 plus 4.2849 joules to get the total energy to be 5.76 joules. Okay, so at that moment in time, that's our total energy. But there's other ways I could answer this. I know also that my total energy has to equal this. Why is that? This is my equation for elastic potential energy. And I know that at the special moment when I'm at my maximum amplitude, my velocity is 0. So I have no kinetic energy. All my potential must be elastic. All my energy must be elastic. And the x in my potential energy equation, I can just plug in my amplitude. And so it turns out when you use this equation, you get exactly the same answer, 5.76 joules. And finally, we can solve this one last way. I can use this equation, 1/2 mv max squared. Because at the moment this passes through equilibrium, there's no potential. All of the energy is kinetic. And I know that velocity. I figured it out earlier. Where did I figure that out? I figured it out over here. So if I plug in that number to this equation, I get exactly the same total energy. So that's just really good confirmation that our total energy is conserved. Okay, part O, what force does the cart experience at time equals 0? Well, we have an equation for force of a spring. And that's the only force affecting the motion of this cart. Is the spring force or elastic force. So if I know the spring constant that was given to me in the problem, and if I know my position at time equals 0, I can know my force at that location. And the position at time equals 0 is what we found again in part H. And so I just plug that in, negative 0.1514 meters. And so that gives me my force at that moment in time to be 19.38 newtons. Okay. Part P, what is the acceleration of the cart when it is at x equals 0? Okay, so this is a little bit of a trick question because conceptually we know that when we're at x equals 0, we're at an equilibrium point. Therefore, that's 0, our position is 0, the force must be 0, and therefore the acceleration must be 0. So we can answer that right away. The acceleration is equal to 0. If we wanted to, we could use the same equation we derived earlier, a is equal to minus omega squared times x, to directly plug in x is equal to 0, so this must be equal to 0. Okay, and part Q, what is the acceleration of the cart when it is at x equals 0.1 meters? Well, we can use this equation, and if you forget about this equation, well, we just use F equals ma. Again, the force is equal to the spring force minus kx, and so we very quickly derive the acceleration is minus k over m times x. We know k, we know m, we know x in this problem is 0.1. We can plug in an answer. We can also recognize that k over m is equal to omega squared, and we can plug in our omega and our x. Either way, we get the same answer, negative 6.4 meters per second squared. So that's every answer to this worksheet. As you can see, we answered, I think, 17 questions, all based on this one equation they gave us at the beginning. So you can see from very little information in oscillation problems, we can answer a lot of questions. So yeah, thank you for your attention.